So, welcome everybody welcome this morning. Today we're going to watch the very first of what's going to be a global concrete webinar series. Today we'll be discussing inspection of PT ducts. Are they grouted, or more importantly, are they not grouted? I'm Shirley Underwood. I'm General Manager here at PROCEQ UK, and I will be your host for this morning. So what we got in the plan for you today? Well, the very first thing you're going to meet is my colleague Tristan Craig Tyler. He's our field application engineer. He's going to give you a brief introduction to GPR and pulse echo tomography. Then zooming in all the way from Torino, you have Guido Tronca, who will be discussing the beauty of why combining both GP 8000 and the PD 8000 is so complementary when testing PT ducts. Then you'll meet our second guest speaker, that's Steve Neville from HDA. He's going to give you some real life examples of his experiences on site, detecting voids in PT ducts. And then in section 4, we're going to do a quick poll. So just if you could answer some questions quickly. And then we'll also give you the chance to ask any questions to our panelists. So at the bottom of your screen, you will find a Q&A box. If you can just type in your questions in there, and we can address them at the end of the session.
I'm going to take you over the basics of ground penetrating radar and ultrasonic pulse tomography today. So without further ado, I'll get started. So here we have the PROCEQ range of instruments for concrete, and today specifically we'll be looking at the GPR Live series and the Pundit Live Array series. So just to be specific, that includes the GP 8800, that's our small GPR for hard to reach areas and curved surfaces, etc. The GP 8000, that's our standard concrete GPR, market leader over here in the UK now. And lastly, but not least, the ultrasound pulse echo technology, the Pundit Live Array series. This is called the PD 8000. So let's just have a quick overview of how these two technologies work. So we'll start off with GPR here. It's a transmitter and receiver. So here we have the antenna. It's placed on the surface of the concrete. It sends down lots of signals. As these signals hit a boundary of discontinuity, it populates something called a hyperbola, and this denotes the presence of a rebar. So for the ultrasound pulse tomography, here we have the same bit of concrete, but we'll see something slightly different. So we have a similar situation, and we send the signal via a transmitter and collect it via a receiver. And this also basically reflects from a boundary of discontinuity, or in this case, the back wall of a slab. If we stitch many of these signals together, these A scans, what we can do is produce a B scan image here. And as you can see, the boundary of discontinuity, in this case, the air at the back of the slab, is quite clearly highlighted. So the outputs from these two instruments. So both of the instruments give you a B scan or a cross-section view. In the case of the GPR, you have both the migrated and non-migrated version. You can also produce a C scan, or a bird's eye view, or an eagle eye view, should I say. You can also produce that into a 3D model, all of that live on site. And last but not least, if you want to project that 3D model or the C scan into the real world, you can do that through our augmented reality software. So let's look at the types of things that you can detect with this instrument. So you've got rebars, objects, which might be things like ducts or pipes, thickness of slab, defects, so that might be honeycombing or spalling. And if we come to a theoretical example of that here, if you look in the bottom left, you've got a nice key here showing you the back wall, rebars, ducts, cracks, delaminations. And traditionally, if you were to go on site and you were to use a pulse GPR, which is what sort of 90% of the industry did before we produced our step frequency continuous wave system. Here you would get the first layer of rebar quite nicely, usually any ducts or large pipes that aren't too deep, but you'd have some limited detection in terms of finding delaminations. You may be able to detect the second layer of rebar depending on the antenna that you had, and you also have the physical limitations of the technology, so object shadow behind metal or object shadow behind air. And you also have lack of penetration, so you'd miss any deeper targets, no matter what they are. So if we then look at the same example, but we put the step frequency continuous wave antenna on this from PROCEQ, along with a PD8000 ultrasonic tomography, we can increase that detection quite significantly. So we've got all of the cracks and the delaminations, the voids, and the ducts, and also quite nicely the second layer of rebar. We still have some limits of detection in terms of the physical properties, so small rebars on the back face may not be detectable, along with any objects shadowed by, again, metal or air. So just to reinforce this is what you could get, and this is what is now possible. So if we then look at why this is possible, we can break down into two sections. So we have the GPR and the pulse echo here. So GPR reflects 100% off a metal object, whereas pulse echo reflects 99% off an air gap. GPR can't see behind metal, and pulse echo can't see behind air. GPR will travel through an air gap, and pulse echo will travel through metal. So in summary, with GPR, you can see behind an air gap and you can see metal clearly. And with pulse echo, you can see behind metal and you can also see air gaps very clearly. So if we move on to an example of this, here we've got a concrete slab and it's got a delamination in it, a small one, under 1 millimeter small. And we can look at the two data outputs from the two instruments. So on the left-hand side here, you have the Gpr scan, the cross-sectional view. You've got a nice clear back wall continuously across the scan, but not much in terms of the crack. And on the right-hand side here, you have the pulse echo technology, very clear delamination or cracking, and partial back wall there. So combining the two scans together gives you a very clear picture of exactly what's going on within the concrete. This just illustrates why they work so well together. So if I now move this on to the live scans of this example. So here we have a video. First up is the GP8000. You scan it across the surface. And as you can see in the scan there, you've got the nice clear back wall, so you can tell the thickness of the slab, but you've not really got much in terms of a crack there. So we'll move it on to the migrated views. You know, this is the raw data, but still not much to speak of. So if we use the PD8000 now, it's a little bit slower because it's a contact induction method rather. And as you can see on the scan on the top right hand side, you've got partial back wall, but you've also got the delamination or crack highlighted extremely clearly. So again, this is just to illustrate why these two products used in conjunction with each other can give you the full picture of what's going on inside the concrete itself. And with that brief introduction to the product, I'm going to pass you over to the experts now, and they're going to take you through some selected applications. So I'll pass over now to Guido Tronca. Thank you very much for your time, and if you have any questions, please feel free to pop them in the chat for me at the end. Over to you, Guido.
Thanks a lot, Tristan, and thanks to all the friends at Screening Eagle for the opportunity of being here today. My name's Guido Tronca. I've been in the NDT business for a while now, starting from the late 90s, coming from an academic background of material science, then focusing on NDT among investigation company and testing lab, then joining PROCEQ for 5 years of nice and intense development, and before being here today as a freelance consultant and service provider. Now, I'm personally very fond of these two techniques that I saw in the past years. They can be labeled as imaging techniques, meaning the ones that really visually give you the inside of what's inside the object. How do they do that? They're both echometric methodologies. They, as Tristan mentioned, they shoot some impulse into the body and listen to its reflected component. What is that in physics that causes a reflection from within a body that, if it was totally homogeneous, wouldn't bring back any information? Well, it's the contrast between two materials. The higher the contrast in property, the more different these materials are, the higher will be the reflected component, and the lower will be the transmitted component. So, the difference between GPR and ultrasound. GPR is using an electromagnetic wave. Hence, it will feel the difference into the dielectric properties of the material. You can imagine them as a conductivity. The more different those two materials are, the sharper will be the reflection. Total similar scenario for ultrasound, but in this case, we are looking at an acoustic impedance difference. Read it as density. So, narrowing down to our field, which is actually concrete, we can imagine a word made of concrete and air geometrical boundaries or defects, and on the other side, the steel reinforcement. Okay, just in key point is concrete is electrically more similar to air rather than steel. Hence, when a concrete-air interface is met, only a partial reflection will occur, allowing the wave to pass through and investigate further. At the same time, when we bounce against a steel interface, we will appreciate a total reflection, hence giving us the best sensitivity to that kind of object. While when we use ultrasound, we're looking at acoustic impedance. Okay, acoustic impedance or density of concrete is much more similar to steel than it is to air. Hence, when we bounce an acoustic wave against an air boundary, we can expect the maximum sensitivity and the 100% reflection, while a steel interface will allow part of the wave to be transmitted. Enough for physics. That was only to justify our statement and our key application. So GPR will be a killer for locating metal objects, and will enjoy the pleasurable benefit of not suffering an air interface. Wheel was invented for a reason, and we all like to scan even at a given distance from the surface. While ultrasound will give us insight even beyond heavily reinforced structures, while presenting at the same time the highest sensitivity to void crack delaminations. If we look at the other side of the medal, then what I see best will make me blind below. So I won't be able probably to penetrate through heavier reinforcement, or my penetration depth will be significantly reduced. And as Tristan beautifully showed before, small delamination can be unseen by GPR. It will also be affected by the water content or conductivity. Fresh concrete, drenched concrete will leave us less penetration depth, while ultrasound will suffer any first interface of air. We need to couple it against the surface. It won't have to be used as rebar locator for sure, and we can expect a lower penetration in poor quality concrete, porous concrete. Okay. Narrowing it down further to our key application today, which is PT duct inspection, we can expect on this kind of scenario the rebar systems to be very sensitive to all the metal, both in the strands and possibly in the sheet, so being the ultimate locator for those. While if we aim at looking at voids, then we can't rely on a locator that will be totally blinded by the amount of feel, but we rely rather on a sonic device able to penetrate through the first layer, the metallic sheet, and give us high intensity in case of voids. So, first of all, we want to locate these objects. Here is a typical post-tension beam with its quite common bulb-shaped geometrical shape. First note, when you're dealing with small surfaces like this, you will easily enjoy a small footprint device able to bring you information really to the key points that often are close to the bulb. Okay, just as Tristan showed before, if I look at the raw data, the immediate insight is typically a linear scan. In this case, is performed orthogonal to the strands, so I can enjoy the clear difference between first layer, see a sharp back wall, second layer rebars, both non-migrated and migrated. Well, as life is not always as easy on site, when it comes to complex structures or you want to investigate the full structure, you can enjoy a better imaging. That's where the imaging techniques kicks in. And so just let me shift to the actual real data that I have here on my pad. We are looking at basically the one side of this beam. You can see that in this kind of view, I can focus down to any given depth. So starting from the surface, I can narrow it down and have a clear view of the conventional reinforcement while going down and seeing this curved object that have to be the strands. Okay, that's a nice idea, but let's look at the raw data. So just starting with a longitudinal scan that was taken, you can see even the raw data that you see a number of points that where we cross the strand, overlapping on an overview where you always have the first layer and the second layer. If I want to focus more on the actual position of the duct, let's assume I want a detailed image of these, or maybe I want to chalk them down on the surface. Here is where you can really appreciate the higher resolution of the antenna. Starting from this, if I scroll from left to right, you can see these two objects actually moving along the side, well, that really gives us a first lead on, okay, this must be duct, a second. So again, a first visual insight is often key to have and it is often enough for our need while on site, even for reporting. Real life, I need to communicate to my final customer my first insight right away. So, okay, then I have already, after half an hour testing, I already have something to buy time and keep my customer happy, sending a snapshot. I have this awful Dr. Underwood that is always late and chasing me for draft results. Okay, here we go. I bought time, my customer's happy. Or on the other scenario, I might be totally skeptical, or I have some trouble with my data. You know, sometimes things get complicated. Oh my God, how many objects I have here. Lucky for me, I may have my trusted senior colleague that I want to share the whole project with. So I will, as I always do, I will rely on my friend Tristan and tell me, hey, take a look at this data and please enjoy the whole project that I just took. I worked here. He will see where I am. He will see what I came up with. And he might drive me to, okay, it's enough. We can work on those data. We can fix them. I got enough insight. I can step back on my truck with a definite peace of mind. Okay, further processing. I mentioned this awful customer of mine, Dr. Underwood, late person, arrogant person, always also lazy. So a number of JPEG are not enough for her. Okay, then I will send the data to my colleagues in the office, and they will probably, in this project, if a nice deliverable is requested, assemble all the data in one single project, project the data according to the real location, so that at the end, the first step for a good, better processing is getting to the final volume. Here, my eyes is really helped and guided into the assigning to all the anomalies, all the high-intensity steel reflectors. I can work with all in sections, typically, and start drawing my object. I will always check the raw data. I mean, otherwise, you might be subject to false positives or ghosts. And finally be able to deliver an AutoCAD compatible draw to my pain in the neck, Dr. Underwood. Okay, phase one done. I located them and I drew them on site. Now I want to investigate whether about the defects. One of the possible workflows that I normally do is the so-called stripe scan, meaning I will collect several line scans along the duct, gathering all the single lines where I will locate my object, in this case, a duct. Okay, what I notice is that I might have low intensity areas, high intensity areas that can be immediately displayed in the app by means of a similar time slice as what we saw before. Okay, and I will label. I will have a reason to start drilling and performing direct inspection. High intensity void is one of the symptoms, as Steve will shortly display, of good reasons to investigate and find the voids. Okay, I think that's all from my side right now. I'll be available for questions and answers. But for now, I will pass to Steve and to you.
Thank you very much, Guido, and thanks to Screening Eagle for inviting me along today. Just a few words about myself. My name is Steve Neville. I work for a UK structural investigation company called Henderson Thomas. I've worked here for 13 years. I've managed many large-scale structural investigations, and in particular post-tension special inspections, which we call PTSIs. Today, I'm just going to talk to you about, over the years of myself and my colleagues carrying out these inspections, the older techniques, and how we're now utilising ultrasonics and GPR in our investigations, as explained by Guido and Tristan. Just trying to move on to the next slide. Just bear with me, sorry. Here we go. So typically the main defects in terms of post-tension in structures is to do with the grouting at construction phase. So the aluminium sheaths that house the actual strands themselves, duct will have been poured into the sheaths themselves, and it actually protects these strands from corrosion and also transfers the stresses from the strands themselves to the concrete, and in this case the bridge deck. So when we receive a specification to carry out a PTSI, the client is usually concentrating on critical locations. So I'll just get my laser pointer. So here we've got the midspan of the structure, which is high levels of tensile stress. That's a critical location. You've got sections such as half joints around the piers where the profile of the tendon rises, and due to the construction process of the grout, often at the high points is where you'll find voids within the duct itself due to gravity. If it hasn't been grouted enough, the grout will seep down here, leaving these locations potentially ungrouted and could be corroding inside. So this is a typical specification drawing that we might receive from a client. It's got other testing procedures such as Schmidt hammering, concrete test panels, but in yellow here they've highlighted critical locations. This is two post-tension parapet edge beams and a cable stay structure. So they wanted us to go in and open the ducts up and look inside to actually see the quality of the strands and whether they're grouted or voided. So in the UK, we generally carry out inspections every 3 to 6 years or more if there's known problems with the structure. In terms of post-tensioning, we're looking for defects such as leaking through joints near the anchors, deflection of the bridge, and cracking is quite high on the list, particularly longitudinal cracking. Example on the left here, you can see these red lines were hairline longitudinal cracks on a tunnel that we carried out an investigation on in Ireland. It turned out that after the investigations, these cracks were lining up with the post-tension ducts themselves, but fortunately there wasn't any defects found when we actually opened up the ducts. But the key thing to remember is if an inspector carries out an on-site visual inspection of a post-tension structure, it can often look fine on the outside, but the defects are actually hidden. So you can't tell what's going on inside the duct. So it could get signed off as in perfect condition, but without knowing what's going on inside the PT duct, which is effectively holding that structure up, there's no way of knowing until we've come across some of these newer technologies and ways of determining that. So just to give you an insight into the potential corrosion that can occur inside these ducts, these 3 images were taken after only 6 years of a post-tensioned car park was constructed. So we're looking at close-up views of where we've chiseled out the concrete and exposed the ducts. This is the aluminium sheath, and you can see here we've peeled the sheath back. Top left here is a low risk. So this is what you want to see if you're an asset owner. We peel the sheath back, it's fully grouted, the strands are nice and clean, and that'll be fine for many years to come. And as I say, these are all from the same structure. This was what we class as medium risk, so there's no grout in here. You can actually see the tendons themselves quite clearly. Corrosion process is starting. You can see some corrosion staining, but you know, generally it's still doing giving the stresses it needs. But this middle image here, this is classed as high risk. So when we actually opened this up, the tendon sheath itself was non-existent. It had completely corroded, and it's exposed heavily corroding tendons. But on the surface, the concrete looked in good condition. So no inspector would have known that this was actually occurring until we actually opened it up. So fortunately, I didn't have a shower this morning when we were opening up this duct, and we got a surprise when about 2 litres of water came out of it. You can see here, we've opened the sheath. There was water sitting inside the tendon, which is going to cause heavy corrosion over time. So that's a real bad defect. Here's another endoscope survey that we carried out 2011 on quite a well-documented structure in the UK. It was Hammersmith flyover. So we're looking here with the endoscope at close-up of the strands. You can see here, this one here is completely snapped, and this one here. And there's a lot of hessian that should have been removed at construction. And the theory was that that was sucking in water to the middle of the tendons, which was inhibitor of the corrosion occurring. There was monitoring systems put on this structure, and evidently it actually ended up having to be closed down. Oh, I've kind of lost where we was. Apologies for that. Just let me get back to where we were. So that structure we were looking at was actually closed down and had to be externally post-tensioned. You can read a good document in the Syria Guide for Hidden Defects in Bridges. So I'm just backtracking here. So in terms of locating the tendon ducts themselves, before GPR and ultrasonics, what we'll get onto, we really didn't have much information other than the as-built drawing. So this is an example of quite a good as-built drawing here. So you can see the tendon profiles, and we had to measure off soffits, off of joints, off of abutments to try and work out exactly where the tendons were and try and find them. And unfortunately, as we all know, the drawings aren't often up to that standard. So here's an example. It must have been scanned multiple times over the years. You can't really work out the numbers very well, and it's hard to see the actual profile of the ducts themselves. So you're really going in blind when trying to locate these ducts. So the only tool we did used to have in our arsenal was a cover meter, which is effectively a metal detector using eddy current technology. Very accurate at detecting the first layer of rebar and accurate at determining its cover. But as you can see, the sheaths themselves here are deeper than this first layer, which is always the case. So it will give you it'll give you the rebar pattern of that first layer, but in terms of finding the ducts, it wouldn't really assist at all. So what we had to do, using the as-built drawings and relying on that being constructed to as was supposed to be, we had to carry out a method called stitch drilling. So we'd use a 25mm diameter drill bit and effectively pepper the element with drill holes, and we'd be hitting reinforcement, and then finally we might hit the sheath. And you know, you have to be an experienced operative to know the difference between the rebar and the tendon sheath itself. So it's time consuming. You're adding unnecessary damage to the structure and vibrations to the operatives and time. You can see this is an example here. I'll just explain what we're looking at, this picture on the right. This is where we've excavated out the road surfacing onto the top of a, we've got to the top of the concrete deck. The blue color is the waterproofing. And then we've had to drill a number of holes using the stitch drilling technique. I'd say about 15 holes there till we've actually encountered the duct, and then we've actually overcored it. This picture on the left here is a view down that core hole, and you can see the top of the sheath itself. So, you know, a lot of unnecessary damage to the structure there due to location. So moving on to newer technologies, and this is just primarily locating ducts. Like Tristan and Guido have explained well, we are using GPR, ground penetrating radar technologies, and this is an example of us using PROCEQ GPR Live. So what we've got here, we were scanning a post-tensioned deck. This is a voided cell here, and you've got 6 tendon ducts in the web. They'll be traveling up and down throughout the span, but this is at the pier where they're at their highest. So we've scanned along the road surfacing. You can see the density change picked up by the GPR. This is the top of the road here where my pointer is, and this is the top of the concrete deck. And then clearly, as Tristan was explaining, the hyperbolas show up the actual tendon ducts themselves, so we know where they are. And it's even showed here nice and clearly the bottom of the bridge deck getting thinner towards its edge, as you can see in the drawing here. So you know, it's reducing this damage and need for stitch drilling. And here's a quick example of a scan. This was carried out on a parapet edge beam. So you can use different colors, you can bring the gain in and out. It'll go to about 800 mil. So for our post-tension inspections, that's more than enough. And you can see here it's picked up the first layer of reinforcement, and then really clearly picked up the embedded post-tension ducts. So you've got the ability on the iPad to actually label it up, so it's all ready for a report. And as Guido showed you, I could send it off to my client, or if he was a junior engineer and he wasn't sure, you can send it back to a more experienced engineer in the office just to check that everything's going on right on site. And the great thing about this processing on site is we're often working on motorway closures, on railway. We might only have 3 hours to carry out the work, so it needs to be quick, it needs to be precise. We can chalk it up on site, get our work done very quickly. This is an example of that scan I've just showed you here, and the output with us marking it on the actual surface. So you can see it's very highly densely reinforced. These were actually about 30 mil diameter bars. And you can see in yellow, this is the reinforcement layer. And what we've done in blue is we found the profile of the tendons themselves, and we've been able to overcore the tendons just to open them up and look at their condition. Nice and neat. You know, not many unnecessary drill holes there. We know where we're going in due to GPR, and you know, we've got all of that done in one shift on a motorway closure. So just to quickly show you how we present some of our results. So picture-wise, we often take a picture of the sheath when we found it, then we peel the sheath open, and this is one was fully grouted, so you take a picture of that, and then we carefully chisel away to view the condition of the strands and collect some of the grout sample for subsequent laboratory testing. A lot of time and money is spent in getting us to the face of the structure, hiring mutes and closing roads and railways. So we often do a concrete test panel involving half cell, minimum cover, carbonation testing and chlorides, just to get a better feel for the structure. And then just down here, we record the details and locations. So that's explaining how we actually find the ducts. And in the last couple of years, we've been using newer technology in the form of ultrasonics and the Pundit Live Array Pro, which you can see my colleague is inside a bridge cell using. Now, as explained in previous presentations, the GPR wave won't penetrate into the duct itself, so we can find them, but we still have no idea through NDT the actual condition, if they're voided or not. This is where the ultrasonics will penetrate through the aluminium sheath and give us a reflection from any voids. So it gives us a locations to home in and do our opening up works. So rather than just having a specification saying open up here, here and here, we can then trace and scan the tendons and go in at locations we feel there's a higher chance of there being a defect. I'm just going to take you through a project that we've carried out and the processes that I do on site to get the results that we need. So initially, you need to calibrate the gains and calibrate the actual ultrasonic unit. So the way that we do this is we actually GPR to locate the tendons, draw them on chalk, and this was carried out from inside a segmental post-tension bridge. So this is a cell, so we can stand in this section and scan the web here. You've got the tendons in the webs. So what we'll do is offer the pundit up to the concrete, but off the tendons. So we're doing it below the tendons. And what I'm trying to do, I know there's fresh air here at 500 mil. So I'm just calibrating that to pick up that air as my calibration. So this is the result of that scan. So we're scanning from here. It's the waves are reflecting back off of the air and coming back and giving me a nice reading at, there you go, 490 mil. It does reflect back 43% of steel, I believe. So this is picking up the reinforcement as well. So once we're calibrated, we're then ready to trace the tendons and determine where we think potential defects are. This is a quick video of my colleague carrying out a scan on a post-tensioned beam. So what he's doing here is just tracing along the, sorry, it's a bit blurry, but he's basically tracing along the tendons that we've marked up in chalk. And what we do is we put a 210 mil mark on the concrete, and that's the width between the transducers. So we're getting a lot of data quickly. I know Guido explained that you can use a stripe scan and AI technologies, which is excellent, but sometimes if we need to get a lot of data quickly, we're doing it just along, doing it live, and we're getting good results quickly. I'll just take you through this project. So we scanned the tendons here. This is the profile. And then in the first shift, we used the pundit and collected all the data. The next day, I reviewed the data and found that we had 3 different scenarios occurring. So I'm just going to take you through those 3 scenarios. And what we do is to get real accuracy and confidence in the results, we open up on a number of locations to see repeatability. It gives us more confidence in what we're actually finding. I would never just go off of raw scan data. So this is the first scenario here. So you can see I've upped the gain a bit here. So we're actually picking up the tendon quite clearly. Nothing's really jumping out. This was a typical scan on this structure. And as you can see, we opened it up here at these types of feedbacks a number of times. We're getting a fully gratted tendon. They're slightly corroded, but they probably went in like that at construction, left on site potentially for a couple of weeks. So that was the good scenario. And the bad scenario for the asset owner is when you're seeing tendon ducts like this. So you can see here, these ducts are completely voided. Not any grout has got to them at all. The strands are corroding. And what we were finding was at these instances where these were voided, the actual signal was completely dropping off. So we believe that the signal is getting to that void and it's scattering, so it can't make it to the back wall, it can't make it back to the transducers. So it was just giving us this dark blue reading, which was very consistent each time. And at all, pretty much all of these locations we opened up, we were finding this type of void. So we were getting good confidence in our results. And the third scenario was we're getting feedback here. So we opened up at this location. Obviously it stood out to us. What we found here was between the actual sheath itself and the face of the concrete, there was some poorly compacted and voided concrete. This has given us these big reflections here, so we knew what was occurring in that scenario. So that's basically me taking you through how we carry out some of our investigations in the UK on post-tension, but it's not just used for that as an application. I'm just going to end with taking you through another example of using the pundit in different scenarios. So our client came to us. They were building a very large warehouse. The concrete slab was 350 mil thick, ground bearing, with a small fabric layer at the bottom. Concrete all looked fine, and then the operatives were drilling holes to bolt in large racking units, and on the odd occasion they were dropping into large voids, which triggered alarms. So from my understanding, a few companies carried out ground penetrating radar surveys, which in a fibre reinforced slab is not worth getting your GPR out the van. It's just going to give reflections back due to the physics and not give you any outputs. So we requested that we carry out a trial on this, and it worked really well. So here you can see on the left, this was where we were finding good quality concrete. So that fabric layer at the base of the slab, so this is the top of the slab here, this is the base of the slab, we were picking it up actually with the ultrasonics and nothing in between. So the signals bouncing back to the transducers from the bottom of the slab with no other voids or defects, and that was good quality concrete. And like I say, to calibrate this, we carried out a number of drill holes just to get confidence in our findings before we didn't need to do that when we were carrying out the rest of the slab. Here we were finding small clumped fibers together, so very small voids, not really massively damaging for the durability of the slab itself, but this is what we were finding in these sections here. So you can still see the back walls giving us a reflection. It's finding its way around these small voids, but then the poor quality voided concrete, this is what we were finding. Like in the PT ducts, the signal's dropping out. It's not getting a reflection off the back wall, so it can't get through the void and it can't get back to the transducers. I'm just going to finish with showing you the picture of where our client cut the slab out to make repairs. And you can see here, this was the voids that we were hitting and we were getting that output. So very large voids here. We think the fiber was clumping on the actual reinforcement layer and then not letting the concrete get through. So that could have been very damaging. Saved our client a lot of money, not having to replace the whole slab. We could identify where the problems were and they could locally repair them. So thank you very much for your attention.